Welcome back to this lecture series on pulse width modulation for power electronic converters. So, this is a lecture series of 40 lecture series and this is the concluding lecture. So, we had 13 different modules and the last module has been on multi-level inverters for pulse width modulation for multi-level inverters, and this is the third lecture in that module and this is the 40th lecture in the entire series. So, I welcome you to this concluding lecture of this series of lectures now. So, it would be good to take an overview of what we have been doing here. So, in the first set of modules we basically covered the different topologies, where this is where we discussed the basic neutral point clamped inverter topology as well, and we looked at different applications in a couple of 2 or 3 lectures. We looked at what were the applications and we looked at things like motor models and how you can model the mains as seen by the inverter and so on. Okay, we looked at the fundamental and the harmonic equivalent circuits etc. Then this module set of modules, they normally they pertain to the PWM generation. So, we looked at Fourier series and waveform symmetries and so on, and then pulse width modulation at low switching frequency, particularly how would you do selective harmonic elimination, and we looked at such things here and the effect of these switching angles on the harmonic voltages, the fundamental and harmonic voltages we tried to study, and we will designing some low frequency PWM methods. Then we looked at triangle comparison based PWM and space vector based PWM, where your assumed switching frequency or the inverter switches at a frequency much higher than the maximum modulation frequency of the inverter. So, this set is broadly on the PWM generation, and then this is all on the analysis part, and this is all about the 2 level inverter. So, there is here also we considered essentially the PWM generation for 2 level inverter. Here also we have been looking at the analysis for the 2 level inverter. How do you calculate the RMS current ripple, how do you calculate the DC link current, and then some ways of estimating the ripple torque that is there, whether it is when you are running an induction motor from sinusoidal voltage, there will be only a steady pulsating torque, but you are feeding it from an inverter, there is not fundamental component alone, there are also harmonic components and they result in harmonic fluxes and harmonic currents. The fundamental flux would interact with harmonic currents and the harmonic fluxes would interact with, the fundamental current would interact with harmonic fluxes and produce pulsating torque, and this we did some analysis on this also, and then we went about evaluating the inverter loss. So, many of the first 3 particularly these are all actually more or less directly extendable to 3 level inverter also. So, here there are some effects of dead time and over modulation, and now we have been into the last module on multi-level inverter. So, as I have said in the previous lecture, so these are the contents that we had in the present module. So, we initially reviewed the neutral point clamped inverter topology and we looked at the pole voltages, line voltages and line to neutral voltages, how they are related here, and the essential difference here is that in a 2 level inverter the pole voltage can be only plus VDC by 2 and minus VDC by 2, and here it can be plus VDC by 2, minus VDC by 2 or 0. So, this intermediate voltage level, it leads to many more voltage levels, like 5 different voltage levels for values possible for line to line voltage, and again more possible instantaneous values for line to neutral voltage, and this is what is responsible for the improved waveform quality. And voltage vectors, they are produced by we have about 27 inverter states. So, the 2 level inverter, like once we understand 2 level inverter and the basic concepts, dealing with 3 level inverter is not at all a problem. So, in 2 level inverter we had 2 raised to the power 3, 8 inverter states. Here we have 3 raised to the power 3, 27 inverter states. For each inverter state it is possible for us to look at what the pole voltages are, which we did, and then correspondingly we can find out what those line to line voltages are, and correspondingly we can find out what those line to neutral voltages are. Once you have these line to neutral voltages, you transform them into the stationary reference frame alpha beta, and you get your voltage vectors, and these would be the voltage vectors produced by 3 level inverter. What we found was, in a case of 2 level inverter there are 8 inverter states, they produce 6 active vectors and the 2 zero states produce 1 zero vector. So, 8 states produce 7 distinct vectors. Here we found 27 states producing 19 distinct vectors. So, there is a lot of redundancy. What do you mean by redundancy? There are more number of inverter states producing a particular vector state, voltage vector, then you call it redundancy. Now, if you have a vector, a particular vector, let us say the vector is of length VDC and it is angle 60 degree. It is uniquely possible, it is only one unique inverter state might be possible. Let us say another one, you have 0.5 VDC angle 60 degree, that is the vector. So, that vector symbolizes 3 phase voltages or the line to line voltages. So, that vector it is possible to apply using 2 different inverter states. So, that is redundancy. In the case of 2 level inverter, we discussed this at length. What is the redundancy? The redundancy is in the 0 state. The 0 state, the 0 vector can be produced using 2 different 0 states. Here the same 0 vector can be produced by 3 different 0 states, and also there are 6 vectors of length 0.5 VDC. They can be, each of them can be produced by 2 inverter states. So, the redundancies in a 3 level inverter are much higher than what you have in 2 level inverter. So, in 2 level inverter you can design so many PWM methods, in 3 level inverter you can design much more than that. So, what we are trying to look at is just some idea, how possibly you can do this, some ideas that will get us going. And please bear in mind what I am talking is, it is actually only the starting process. I mean it is not a not a final thing. These are all inputs, enabling inputs for you, so that you can do further, and you can do more work on pulse width modulation, or work on PWM converters in various ways. So, we are just trying to get some introduction, some basic idea on how exactly you can do that now. So, remember we had so many lectures we discussed about PWM for a 2 level inverter. So, if we extend that in 3 level inverter offers much more possibilities than that. So, you have much more things are actually possible in a 3 level inverter. So, we are just trying to understand the fundamental concepts, so that we will be able to deal with analysis of some known PWM methods, or probably come up with some new PWM method design or whatever. So, that is what we have been trying to do now. So, everything you did, like sine triangle PWM we did for single phase, I mean for a 2 level inverter, we tried to extend it for 3 level inverter. In the case of 2 level inverter, it is fairly simple, because sine triangle PWM there is one sinusoidal modulating signal for a phase, you are going to compare it with a triangular carrier. So, its output is going to be giving you the gating signal, top and bottom devices are complementary. Whereas, if you go for 3 level inverter, the same sine triangle PWM, you may have one modulating signal, but your inverter leg, your R phase leg is not having only one, it has actually 2 sets of complementary devices. So, you need 2 gating signals. So, one of them we saw that the same sine PWM, I mean you can, one possibility is you use a modulating signal, single modulating signal, and compare it with 2 level shifted carriers. This is one possibility. As I mentioned to you, the other possibility also exists, that is you use 2 modulating signals corresponding to a particular phase, R phase, and compare it with a single triangular carrier also. There is such a PWM method also. I am not discussing that PWM method here, and that is covered in some of the references that I have already indicated to you. Alright. So, now this is one way of extending to 2 level shifted carriers. So, if they are level shifted carriers, what do you mean by that? So, your modulating signal earlier in sine triangle PWM, for 2 level inverter, we considered the carrier to vary from -1 to +1. Now, what we do, we have 2 carriers, one would vary from 0 to +1, other one would vary between -1 and 0. So, these 2 level shifted carriers, and again it is not necessary that they have to be in phase, they could have some phase difference also. So, we looked at this in phase and the out of phase issues now. This comes because of such kind of thing is not there in 2 level inverter, you use a single carrier only. You use such ideas, for example, when you go when you talk of parallel inverters, when you have inverters connected in parallel to the grid or running a motor, sometimes what you do is you do the so called carrier interleaving, that is you have 2 inverters, they are connected in parallel to the grid through, let us say, line inductors. Then what you can do is one will be compared with some carrier at some 5 kilohertz, other one will also be compared with the modulating signals or will be compared with a carrier at the same 5 kilohertz, but these 2 carriers will have a small phase shift like 90 degrees or 180 degrees at the carrier frequency. This idea of that carrier interleaving is a very interesting idea that has been used extensively in parallel converters. Now, what we are trying to do is in the same leg only, the same sinusoidal signal, you can have level shifted carriers. There is no real advantage by doing this in many cases. You can actually use out of phase, but as we just discussed in the last lecture, in phase level shifted carriers are better than many other possibilities. So, like they give you a low harmonic distortion. Okay. Then we looked at the switching sequence. So, we want to see what inverter states are getting. What do you mean by the switching sequence? We are looking at the state in which the different inverter states are, the states are applied when you use a particular PWM method now. This is actually the link between your triangle comparison based PWM and the space vector based PWM. So, there are 2 different approaches and you actually link them nicely by doing this now. So, you consider any carrier comparison PWM method. So, what you do is look at one carrier cycle or look at one sub cycle and see what is the switching sequence like. and so that gives you a very good idea of how it is going to work now. So, you can compare it with some space vector based PWM methods more easily, and once you know that, doing this analysis, you know the voltage vectors that are getting applied. It is a carrier comparison PWM, but you know what is this, what are the voltage vectors getting applied and in what sequence they are getting applied. So, you can calculate the error voltage vector and you can integrate, and you can do those analysis like the stator flux ripple analysis which we did earlier. So, we ended, in the last lecture we had some things on the switching sequences for the in phase and out of phase SPWM. This is what we looked at, and the switching sequence for third harmonic injection is pretty similar to that, and what we found out was in many of these cases, when you use in phase PWM particularly, the 3 nearest voltage vectors are the ones that are often getting used. So, that is what comes up, whereas in the out of phase cases it is not the 3 nearest voltage vectors. That is one significant finding there. Then like in the sinusoidal PWM you can add third harmonic, you can also add some other common mode signals which would lead to bus clamping. This is what we looked at towards the end of that in the last lecture, and we would be looking more in terms of space vector based PWM, 3 level inverter controlled as equivalent 2 level inverter, and so on so forth, and more number of topics that we would look at today. So, when you do this, what you essentially are doing is this 3 nearest vector, what happens is, what are the 3 vectors, if you look at the sequence in which they get applied, you normally start from one vector whose magnitude is 0.5 VDC and you come back to the same vector, and that vector we call it as the pivot vector. This is equivalent to your 0 vector in a 2 level inverter case now. So, this pivot vector time is divided differently, just like the 0 vector time is divided differently in a 3 level in a 2 level inverter. This pivot vector time is divided differently by different PWM methods in a 3 level inverter. In conventional space vector PWM, you divide this pivot vector time equally between the two now. And if you really see that the pivot vector time is alright, you can apply either pivot state 1 or pivot state 2, there are 2 pivot states, but they have some influence on the DC voltage unbalance. That is something we will take a look at now. And you can look at the effect of pivot state on the DC voltage unbalance, and we will also quickly see how you can work out, you can evaluate the DC link current for a 3 level inverter as we try to evaluate it for a 2 level inverter. And we would look at bus clamping PWM from the space vector point of view now, because when you use the pivot vector divide, you are using 2 pivot states, here you will be using only 1 pivot state, just as in 2 level inverter you used only 1 0 state instead of 2, here you will use only 1 pivot state now. And we will do this advanced bus clamping PWM which we discussed for 2 level inverter. We will see how this can be extended to 3 level inverter, and then we will go on to see the error. We will look at the error voltages in the various cases, and then we will try to integrate, you can once you understand that, you can integrate and get the stator flux ripple and do an analysis very similar to what we did before, and possibly we will just see how you can start coming up with hybrid PWM methods here also. Alright. So, this is PWM for 3 level neutral clamped inverter lecture 3. So, third lecture in this, last lecture in this particular module. So, this is 3 phase 2 level voltage source inverter. Each leg is a single pole double throw switch, and they are relays like this. These 2 switches, they switch in a complementary fashion, and the switches can block voltage in one polarity, the collector positive with respect to emitter, and they can conduct in both the directions. The transistor can conduct in one and the diode can conduct in the opposite direction. The 3 level inverter, in every leg, instead of being a single pole double throw, it is now a single pole triple throw switch. The throws are connected to the positive bus, negative bus, and the DC neutral. Here also positive, negative, and the DC now. Is that fine? Alright. So, now you have one leg of a 3 level inverter which has been realized here. So, this is something we looked at in the first module, and we also looked at, we briefly looked at this in the subsequent the past 2 lectures in this module. So, this S1 and S2 and S3 and S4, when both are on, R is connected to the positive. When these two S3 and S4 are on, R is connected to the negative. When the middle 2 are on, R is connected to the midpoint. So, you find that S1 and S3 are complementary and S2 and S4 are complementary. We saw this in both the previous lectures now. So, the PWM requires that we generate the signals for S1 and S2. Then S3 and S4 can be generated as complements of S1 and S2 respectively. Okay. So, this is 2 legs of a 3 level inverter, and if you are using a single phase load for some reason, or let us say there is a single phase source whose power you would want to tap and supply to some DC load, you could potentially do this. Now, this is the 3 phase 3 level inverter which we have been talking about. Now, remember all the space vector PWM, all that are actually valid for 3 phase cases and not really for single phase. For single phase inverter also we discussed some PWM, we looked at some even harmonic injection also in one of our lectures in the triangle comparison based PWM. In that module we discussed one. All the space vector PWM idea and all the third harmonic injection, common mode injection are all ideas which are actually applicable to 3 phase. In fact, they are extendable to 5 phase, 7 phase, etc. also. Alright. So, this is the inverter that we are actually looking at. So, let me quickly indicate the important terminals we will have. So, these are R, Y and B terminals. These are the terminals of the load. You can probably assume that an induction motor R, Y, B is connected here and it has some midpoint neutral which is not connected anywhere. Okay. Alright. So, this is positive terminal, this is negative terminal and this is 0 and you have VDC by 2 and you have another VDC by 2 with this polarity. So, this is a 3 level inverter now. We had already seen this. So, VRO can take these values and this 0 is what you do not have in a 2 level case and these relationships are similar to what you have in a 2 level inverter. Now, again because your VRO is this additional 0 is there, in VRY you have this additional value which is not possible in 2 level, which is possible in 3 level. Again these things are what you do not have in 2 level, but you get in a 3 level inverter. Because of these additional voltage levels being available, so the inverter output can follow the ideal desired output more closely and can lead to improved waveform quality. So, this is what is our voltage vectors now in a basically it gives for a 2 level inverter. We can quickly fill this up to show how it is for a 3 level inverter just as an exercise, plus minus minus. So, you have plus 0 0, it will be half of the length of the vector that corresponding to plus minus minus. So, plus 0 0 and 0 minus minus produce the same set of 3 phase line to line voltages. So, their output this is like this now. Then let me consider the set plus plus 0 and 0 0 minus. So, they will produce a vector half the magnitude like this and again here 0 plus 0 then minus 0 minus and once again I have here minus 0 0 0 . So, I can look at minus 0 0 and 0 plus plus and there is another one, this is 0 0 plus minus minus 0 and I can do this, here it is plus 0 plus 0 minus 0. So, if you know the voltage vectors corresponding to 2 level inverter, extending it to 3 level inverter is quite easy. So, this is all that you have and 0 0 0 minus 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 plus plus plus, they produce the null vector. So, the only other vectors which are a speciality actually of 3 level inverter are here. These are the other vectors. So, I am repeating this a number of times for this is useful, I know. This is plus 0 minus, this is 0 plus minus, here it is minus plus 0, here it is going to be minus 0 plus and here it is going to be 0 minus plus. So, this is how the vectors are, which is fairly simple. So, if you have a 3 phase voltage source inverter, you can do a sinusoidal modulation using 3 phase modulating signals as shown here and these would be the average voltages and this would be the average voltages when you have common mode added and these are 3 phase average voltages, you can come up with the 3 phase average voltages on the load. Vr average, V1 average are the 3 phase average voltages applied on the load. From that you can calculate your V alpha average and V beta average and so all this is possible. So, as we found before, sine triangle PWM for 2 level inverter you need 1 carrier, here you would need 2 carriers. So, 2 level shifted carriers like this is what we do and of course, as I mentioned to you, you can use only 1 carrier, that is what you can do is shift the R phase signal up by adding plus 1 to this. Again whenever this signal goes negative add plus 1 to this, again when this signal goes negative add plus 1 to this, then you can use only the top carrier for comparison. So, this is something that you use for ease of implementation and the result would be the same. But anyway, we are considering 2 level shifted carrier waveforms which are in phase like this for this particular lecture As I mentioned to you already, so you can also have out of phase carriers, and as we discussed in the last lecture, the inverter state sequence is different here. Here you use the 3 nearest vectors, here you use 4 different vectors, and one of the vector is far away from the reference vector, at least one of them. So, the instantaneous error voltage vector is high, which is also shows that the harmonic distortion is high, and there is some detailed study that has been carried out, and in the references that I indicated to you, you can find more details on this now. So, what we would actually do is see, this is what we will do for the implementation, we will shift that, but we will consider the carrier to be 2 level shifted carriers compared with a sine or any other modulating signal here. So, when we looked at the switching sequences in the last lecture, what we found out was, let us say if we are looking at the in phase triangle PWM, it starts from here. So, for some set of 3 phase references, it could start from plus 0 0, it could go to plus 0 minus, plus minus minus, and come back to 0 minus minus, like here and back here. So, this is something, these 3 vectors, and it starts from here and comes back here. Let me just indicate it in terms of arrows. So, it may go like this. Again, in the opposite direction, so what happens is, when the reference vector is sweeping through this region, when the reference vector is sweeping through this region, you can talk either in terms of reference vector or 3 phase sinusoidal modulating signals. If you have modulating signals, you transform them into the space vector domain, it becomes a reference vector. You see this plus 0 0, you see 0 0 minus, both of them lead to vectors of length VDC by 2 and the same vector. So, this vector you call that as the pivot vector, because generally it starts from there, it ends from here, and you call those 2 states as the pivot states. That is, you call those states as pivot states. What are the pivot states? Plus 0 0 and 0 minus minus. Similarly, this is also pivot state, these are all pivot states, that is a terminology that we generally use here now. And pivot vector is like when you say it is 0.5 VDC angle 0, that is the pivot vector we are talking of. That can be realized using 2 states, and now you see this is the redundancy I was telling you. This is the kind of redundancy you had in a 2 level inverter. You had 2 different 0 states, now you have 2 different pivot states. So, this gives you lots of possibilities now. So, in the case of sine triangle PWM, what happens is, you start from here and come back and go on there. With some common mode addition, the time you spend at plus 0 0 and 0 0 minus change, but the total thing does not change. It is just very similar to common mode addition in the case of 2 level inverter. Okay. So, you can add common mode to this, this is what we saw, and if you have common mode, then these 2 times will change. So, that will happen, you will still get the same vector. Again, if you are, let us say you are in a different vector, like let me just indicate something else. Let us say different color maybe, yeah. So, if your tip turns out here, you will see that you will for certain sets of 3 phase references, you will see that these 3 are getting applied, and you will find that your reference actually falls somewhere in between. So, the in phase sine triangle PWM, and where you use these in phase carriers, level shifted carriers, you may compare them with sinusoidal modulating signals, or you can have sine plus common mode. In all these cases, you generally find that the 3 nearest vectors get applied, and therefore, they lead to good harmonic performance. Particularly when you go to conventional space vector PWM, you make sure that these 2 get applied for equal durations of time, and that makes the harmonic performance a little better than what is possible with usually with sine triangle PWM. On the other hand, when I talk to you about the this method, the out of phase would use these sequences which I am circling using blue, and you can see that the error is pretty large. For example, when this is applied, the error is pretty large here, and therefore, it produces a higher amount of harmonic distortion. So, as I mentioned to you, these are some good papers, I mean these are some useful references for you to understand this subject, I mean for this in phase and out of phase sine triangle PWM. and also look at some other triangle comparison methods and try to analyze them. So, as I mentioned, you through 3-phase sinusoids you can add third harmonic component, and you can add suitable common mode components such that the PWM in the phases would be clamped to PWM, bus to one of the buses. So, you can have different continuous or discontinuous modulating signals as you have in 2 level, and in fact more possibilities are there. For example, here 0 clamping is possible, as I mentioned towards the end of the last lecture. That is, in a 2 level inverter you can clamp a phase to the positive bus or to the negative bus. So, you will clamp it to the positive bus in the positive half cycle for 60 degree and clamp it to the negative bus phase to the negative bus during the negative half cycle for 60 degree. Now, you can actually clamp a phase to the 0 bus, that is the DC bits midpoint for 60 degree in the positive half cycle, again for another 60 degree in the negative half cycle. So, such interesting methods exist, and that is what you would call as 0 clamping PWM, for example, you can call them like that, that is also there now. Then you have comparison of 3-phase modulating signals, but what we assume in all these cases, we assume different continuous and discontinuous modulation signals, but we assume that we are using in-phase triangular carrier only, which essentially ensures that we are getting the 3 nearest vectors, and the common mode makes sure that the pivot state times, the division of pivot state times changes, and if you go to bus clamping, what happens, only one pivot state is used, the other pivot state is not used. So, that is what happens now. So, as I said, with third harmonic injection, the switching sequence will be pretty similar as to what we did with sine triangle PWM. Sequence will be the same, the pivot state times would slightly change because of your in common mode addition now. So, your R phase signal here, for example, has come down. So, you have, so your Y and B phases would have also come down by the same extent. So, you will find that a one particular pivot state is applied for longer than the other, and the other one would get applied for shorter time. So, this addition of common mode changes the pivot state time. The total pivot vector time is not changed, but the division of pivot vector time between the two pivot states is changed now. Now, the same kind of 60 degree clamping we used, we looked at continual clamp and split clamp PWM methods for 2 level. Here also you can look at continual clamp PWM waveforms, modulating waveforms, where a phase is clamped continuously to the positive bus for 60 degree and continuously to the negative bus for 60 degree, and here it is between 60 to 120 degree in the middle of the positive half cycle. Here again it is in the middle of negative cycle, it is not necessarily so. This can be anywhere from this can start anywhere from 30 to 90, and the clamping region can end anywhere between 90 to 150, and this can be symmetric, like this can start anywhere from, let us say, 210 to 270, and this can go on all the way till 330, 270 to 330. So, that would be continual clamp PWM, and 60 degree bus clamp PWM is one specific example. So, you compare it with 2 level shifted high frequency carriers. So, you will see that the R phase is clamped here, and again here also R phase is clamped. Similarly, you will have other regions where Y and B phases will be clamped now. Just one example I am giving, there are many possibilities. Every possibility that existed in 2 level also exists here, and more number of possibilities exist in 3 level inverter now. So, when you do this, I am sorry. So, what happens to these sequences, you end up with the same set of sequence as I mentioned before, like you can work that out. So, for this it may start with plus 0 0, go to plus 0 minus, plus minus minus, and go to plus 0 minus minus. So, for our question of convention, let us call this as 0, let us call this 1, 2, and this is 7, like we called in a 2 level inverter. So, this is 0, this is 1, this is 2, this is 7. So, you have these vectors applied for durations T0, T1, T2 and T7. Now, if you consider the same sinusoidal references and add some common mode to that, the V reference vector will not change, because the common mode signals are added, V reference vector does not change now. So, the V reference vector continues to be the same, but what you will find is when you compare the time for which this T7 may reduce and T0 may increase or vice versa. So, that is what you will happen now. As an extreme case for bus clamping PWM, what will happen here is one of them might not be there. For example, you may have only plus 0 0, plus 0 minus and plus minus minus, and the same thing may go in the opposite, the reverse direction, or it could be the other way, 0 minus minus, plus minus minus, and plus 0 minus. This is what you will find in bus clamping PWM. One of the pivot states is not used. You can find some similar observations when you use, let us say, here also. Like you have a different sets of 3 phase modulating signals, the equivalent reference vector may fall here, or you may have equivalent reference falling here. In all these cases, this would be the pivot state, and in this pivot state, I mean pivot vector, and you will see that only one pivot state would get applied if you are talking of bus clamping PWM. And for the kind of bus clamping PWM I showed you, this middle 60 degree, R phase is positive, and therefore this will not get applied. R being R being positive is what will actually get applied. I mean it will make sure that R phase is always positive. Only such inverter states would actually be applied now. So everything that we studied there can be extended here also. So in the case of 2 level inverter, we considered the 3 phase load currents to be sinusoidal, the harmonics were neglected. Here also there is harmonics are neglected, there is still greater reason to neglect harmonics here, because the 3 level inverter produces better waveform quality than that. Then like before, the switching functions, we have to multiply the load current with switching function, but the difference now is the switching function of top device. Earlier there was only one top device and one bottom device in a 2 level inverter. Now here you have S1, S2, S3 and S4, and by top device here I mean S1. What I mean here is S1. So for R phase leg it will be SR1, SY1, SB1. So you have to multiply by, so the switching function is common there and here. You have to multiply it with the switching function, but which switching function? It is the switching function of the top device here. Again then the next thing what you do is you find the currents, the top device currents, the currents through the top devices as in the previous case. The only difference is that it is top, that is the difference. And if you add those 3, you would get your DC link current. So all right. So there is similarity, except that you are going to multiply it by switching function, and then the top device currents are going to be added. So once you do that, you will get the DC link current. So in the DC link current, as before, will have a DC component and it will also have ripple component, and this DC component will flow from the rectifier or the DC supply. And the ripple component, you would expect most of the ripple component to flow through the DC capacitor. Some part can come from there also, but many a times you can assume that the entire ripple component flows through the DC capacitor, and you can go about evaluating the capacitor current, the DC capacitor current. So the same way, like it's just a little more complex, more involved than the 2 level inverter. Otherwise you can do it in the same fashion. So you can once again come up with the RMS capacitor current, which will help you in sizing, and once you have the RMS current, you can also estimate the power loss along with the knowledge of the equivalent series resistance, and with power loss you can estimate the temperature rise and also possibly the life of capacitor. So you can actually it's not about the DC link current, but the rest of the things you can actually for switching sequences for various carrier based PWM and all that, you can actually look at this thesis as a reference now. So let us look at the doing things from the space vector point of view. That is something that we have to look at. That is, what we are doing is we looked at the 3 phase references being provided as 3 phase sinusoids or 3 phase sinusoids with common mode added. Instead what we will do is we will consider the reference as a voltage reference being provided as a rotating reference vector. It is a revolving reference vector which revolves at the fundamental frequency omega, and its amplitude is or its magnitude is proportional to the fundamental voltage we want, and this we are sampling once in every subcycle Ts. This is similar to what you do in a 2 level inverter, space vector based PWM for 2 level inverter. Then you identify the sector within which the sample falls, again same as what you do in 2 level inverter. Now the only difference is the set of voltage vectors to be applied should be identified. In the 2 level inverter it is normally it is the two active vectors, one on the clockwise side of the reference vector, the other on the anti-clockwise vector. So 2 active vectors and a 0 vector. Here you can consider different sets of vectors actually speaking, and you normally consider the 3 nearest vectors now, and finding this 3 nearest vector is some additional job that you really have to do, and that takes certain amount of computational effort now. And once you do that, for each of the 3 vectors, for example, let us say you have identified the 3 nearest vectors, for each of the vector you have to calculate the dwell time, and what can actually happen is, depending on where you are, the formulae may have to be used could be different, and after that you go about outputting the voltage vectors in the desired sequence. So, let us say you are like this now. You have identified, there is a rotating vector which has been sampled, and you have identified that this falls in the so called sector 1. Now, in this sector 1, the tip falls in the so called triangle 1, let us call this as triangle 1. So, sorry, this is triangle 1 formed by these 3 vectors now. So, these are the 3 nearest vectors now. So, you are going to do some calculation. Let us give some names here. This is, let us call it as V1 vector, let us call this V2 vector as before. So, let us call this as V7 vector. So, let us call this as V13, let us call this as V14 vector. Now, what you have to do is V1 vector T1 plus V7 vector T7 plus V13 vector T13 equals V reference vector Ts. This is the old second balance equation. This is a vector equation, so it contains 2 equations. Then the other equation is T1 plus T7 plus T13 equals Ts. The idea of old second balance is still the same. You need 3 vectors now. You used 3 vectors. Now, what you see is actually the 3 vectors have to surround the tip of the reference vector. That is important. You can actually use these 3 vectors also. These were the 3 vectors you would have used as a 2 level inverter. Now, you have another set of 3 vectors, and these are closer to this vector, and therefore, the error vectors are closer, and therefore, their integrals are going to be lower, and therefore, you are going to have lesser amount of distortion in your current. So, that is the basic difference. Now, but you have to calculate this T1, T7 and T13 by solving this. You will get some set of formula in terms of V reference and alpha. You will get T1, T7 and T13, you will get some set of formula if you really sit and do this now. So, now let us say the reference vector was not here, but the reference vector is here. So, what? Now, you will have to use these 3 vectors. So, let us say we call this V1, V7, this is V2, this is V13, this is V14. Now, V reference vector multiplied by Ts, this is the desired volt second, that will be equal to V13 vector T13 plus V7 vector T7 plus V14 vector T14. Then you have T13 plus T7 plus T14 is equal to Ts. This is, from solving this you get the old second balance. This is old second balance. Then you can get expressions for T13, T7 and T14 in terms of Vref and alpha. But you will see that these 2 expressions, this set of formula that you get from here and the set of formula you get from here would be different. This is one difficulty you have. Now, once again let us say you have here, if your reference vector falls in this so called triangle 3, what you need to do now is, this is V7, this is V2 and this is V14. You would say V7 T7 plus V2 T2 plus V14 T14 equals V reference Ts. The idea of volt second balance is still the same, but the choice of vectors is different. So, you have T7 plus T2 plus T14 is equal to Ts. This will give you another set of formulae for calculating T7, T2 and T14, and here this is pretty similar to what you have in a 2 level inverter, except that these DC voltages here, I mean the voltage vector length are VDC by 2. So, once again what you will get is, if you call this as V13, you call this as V14 and you call this as Vz, you have V13 vector T13 plus V14 vector T14 plus Vz vector Tz is equal to V reference vector Ts, and T13 plus T14 plus Tz will be equal to Ts. Okay. So, these are all will be different, and that is going to pose a difficulty, and this if you write down the equations for T13, T14 and Tz, you will find them pretty similar to the 2 level inverter case, except for VDC now will be equal to VDC by 2. This is the difference that you will have now. But so, when it is in these 4 different triangles, you have 4 different formulas. So, there is some difficulty. What is normally done is, you reduce that to an equivalent 2 level inverter. So, these are the difficulties. Each sector divided into 4 triangles, and each triangle is formed by the tips of 3 voltage vectors, and you have to see which vector where it falls, and then calculate the dwell times for those 3 vectors, and you need different formulas. To solve the problem, what you actually do is to deal with it as an equivalent 2 level inverter. So, before that let us take a quick look at the pivot states, which is really our there is plus 0 0 and 0 minus minus, both of them give your same vector, which is 0.5 VDC angle 0. So, now if you look at, there is current flowing to the DC neutral, there is a current flowing into the DC neutral. So, how much is that current flowing into the DC neutral? In this case IY plus IB, which is equal to minus IR, is the current flowing into the DC bus midpoint. When you are applying this state, it is IR is the current that is flowing into the DC bus midpoint. So, what you see is, as far as the load is concerned, the load voltage is concerned, this state and this state do not make any difference at all. They produce the same set of line to line voltages, but as far as the inverter they make a difference. This is something I have been mentioning in a 2 level case also. There it would make a difference in terms of who is conducting, so conduction loss and switching loss. Here also that same thing is valid. One additional thing is that this current is flowing through the DC bus midpoint, which is in a 2 level inverter that connection does not exist at all, whereas in a 3 level inverter that connection exists. Therefore, there is current flows. How much current flows? In this case the current flowing is IY plus IB, which is equal to minus IR. Here 0 minus minus, R phase is connected to the DC bus midpoint, therefore R is flowing. So, you can see that opposite values of current, equal magnitude, but opposite sign flows there. So, they actually have opposing effects on the DC voltage unbalance. This DC current flowing through that, what will it cause? If for example, let us say you have this DC, you have this. Now, through this midpoint some current flows, there is some current flows. Let us call this I neutral, call this as IN for I neutral, and this is going to charge or discharge in some particular direction, and this is going to lead to voltage unbalance. That is, this voltage V1 and this voltage V2 may not be equal. This causes this problem, and the problem is because load current is flowing, and one way to do this is you can look at how they are unbalanced, and you can see that these two have opposing effects on that. One injects current IR, one injects current minus IR. So, this choice of pivot state is also, now you know that this is the cause for voltage unbalance, and this can also be a possible solution for voltage unbalance. You use one state more and the other state less, you have this choice, you can still produce the same reference vector. So, the choice of the pivot state can also be used to some extent to mitigate this voltage unbalances. This is one of the points that I wanted to tell you. Now, coming back to what we are trying to do, this is I am showing a part of the picture. I am not showing all the 6 sectors, but I am showing only this region now. So, if you look at, there are certain things you can always observe. Let us say the reference vector is only within this part, this is region somewhere within this. So, you will see that the R phase is predominantly positive, is R is 0, and you will see that the Y phase predominantly switches between minus and plus or whatever, there is some limited thing. Okay. So, let us say here, now let us look at this hexagon. Let us look at, so this pivot vector is very similar to 0 vector in many cases, and therefore you can look at this hexagon, and this hexagon is quite similar to that of a 2 level inverter's hexagon. So, what you can do is, in every extent you can regard this as an equivalent 2 level inverter. Now, this is your pivot vector. If you subtract the pivot vector, you are going to get some vector. Let us call this as some V beta vector. So, this V beta vector is the equivalent reference vector for a conceptual 2 level inverter. You can view this as a conceptual 2 level inverter. Let us come back to this in a different fashion now. So, here I am just trying to show that sector alone, I am just trying to show that one alone. I am showing only that hexagon which I had shown in the previous picture. I have removed these portions, I am showing this now. So, I have subtracted and showing this V beta vector, and this is at an angle beta. Now, if you look at this, it is very similar to a 2 level inverter. This is plus 0 0 and 0 minus minus are like your 0 states, plus and minus 2 different 0 states, and there are active states here. The only difference is there are more number of states here, and you will see that many of them may not be used. Plus 0 minus, you make one switching, you would go to 0 0 minus, and from 0 0 minus you would go to 0 0 0. From 0 0 0 one switching will lead you to 0 minus 0 and you go to plus minus 0. Some of them you will not use. So, actually this is what you get. Which ones you will not use here? This one is something you may not use. So, these are the ones that you really use here. Now, what is it that is really happening? If you look at R phase, the R phase is either plus or 0. You look at Y phase is 0 or minus. You look at B phase, it is again 0 or minus. So, this is what you get in all these 6 cases. That is what you are trying to say is, let me argue differently. R phase is there, right. There are 3 voltage levels, plus VDC by 2, 0 and minus VDC by 2. Now, this part is the positive half cycle of R phase. This part is positive half cycle of R phase. So, your fundamental voltage, R phase fundamental voltage is positive. So, there is no business for the R phase really to go to minus. It is usually going to switch between plus and 0 only. So, let us say R phase switches only between plus and 0. Now, let us take Y phase. Up to this angle, this is the Y phase 0 crossing actually, Y phase is negative here. When Y phase fundamental voltage is negative, you will want to switch the Y phase only between 0 and minus. Y phase does not really have to switch to positive. So, in its negative half cycle it switches only between 0 and minus, and again you take B phase is negative peak is here, and this is part of the B phase negative half cycle. So, B phase switches only between 0 and minus. So, what we are trying to say is, let us say a particular phase switches only between plus and 0 in the positive half cycle and 0 and minus in the negative half cycle. So, based on this you can divide the entire fundamental cycle into 6 extents. So, in each extent you will find that for example, this is one extent. In this extent you will find that R is switching only between plus and 0, Y is switching between 0 and minus, B is also switching between 0 and minus. So, you can call this high and low, high and low, high and low. So, you ignore plus and 0 for the time being. So, you see that this 3 level inverter is really like a 2 level inverter, because the inverter is never getting connected to the third level within this region. So, what you do is, in every region you start looking at the inverter as a 2 level inverter, but the high corresponding to R phase is plus and low corresponding to R phase is 0 here. But when you look at some other region here, the high corresponding to R phase will be 0 and the low corresponding to R phase will be minus. So, this will change. What is high, what is low, that will change. So, this is high and this is low, this definition will change, but within one extent you can always look at that as a 2 level inverter. So, this is something that you can commonly use. So, you use V beta. Now, this V beta, it is easy like a 2 level inverter. This angle beta tells you in which sector it falls. You can call this as the sector 1, 2, 3, 4, 5, 6 like your older case, and then these vectors, and now your calculation is same. You can calculate your null vector time in terms of V beta and beta. It is going to be V beta by 0.5 VDC multiplied by sin beta by sin 60 into Ts, that is going to be this active vector time. This active vector time is going to be sin 60 minus beta. So, I can write it down if you necessary. You see, you call this 0, 1, 2 and 7, T1 will be V beta divided by 0.5 VDC. Instead of VDC it is now 0.5 VDC, and sin of 60 minus beta instead of sin of 60 minus alpha divided by sin 60 into Ts, and T2 will be V beta by 0.5 VDC sin beta by sin 60 into Ts. So, this formula would be the same. So, your definitions are always like this. So, you would call this as 1 and you would call this 2 in this sector for example. So, you can actually calculate it like this. So, the calculations become much simpler now. So, there are many easier ways of implementing. It has actually been discussed extensively in the literature. This one particular paper is one way of implementing the centered space vector PWM, or the conventional space vector PWM, which involves the null vector time or the pivot vector time to be equally divided. This is one reference for that. This thing of seeing 3 level inverter as inequal and 2 level inverter has also been discussed extensively in this particular thesis now. So, once you break it down to a 2 level inverter, many of our other newer, relatively newer ideas and switching sequences can actually be taken over to a 3 level inverter. Now, you have the conventional sequence. What you do? You start from 0, 1, 2, 7. So, this is the equivalent reference vector V beta with angle beta for that. So, what you really do is you apply 1 and 2 for certain durations T1 and T2 and Tz for the remaining durations, so that you realize this. So, this you can apply this whatever is your Tz, you can apply T0 and T7 for equal durations of time as in conventional case. You start from 0, 1, 2, 7, this is your conventional sequence, where 0 is one pivot state and 1 is some other active state, 2 is another active 2 is another state, and 7 is your back to your pivot state. So, you are starting from pivot state and ending here, again you are going in the opposite direction. This is the conventional sequence extended to a 3 level inverter now. The same way the bus clamping sequence 0, 1, 2 can be extended now. So, let us call one of these pivot states is 0, this is 1, 2 and the other pivot state is 7. You start from 0, you apply the same pivot state for the entire pivot vector time, then this is T1 and T2, that is all. You apply this for T2 seconds, come back apply for T1 seconds and come and stay here for T0 seconds, that is conventional sequence 0, 1, 2. So, 0, 1, 2, 2, 1, 0, you can go around like that. The same way you can do the other clamping sequence also, that is you are now avoiding the pivot state 7. You start from 7, 2, 1, 1, 2, 7. The same way you can go to the advanced bus clamping sequence also, you avoid this pivot state 7. So, 0, 1, 2, 1. You apply this 0 for the entire pivot vector time Tz, apply this for a T1 by 2 seconds, go here, stay for T2 seconds, come back and stay here for T1 by 2 seconds, and you can do the reverse again 1, 2, 1, 0. So, the same way 7, 2, 1, 2, you can start from 7, you can avoid the pivot state 0, you can apply this for the entire Tz, go over, apply here for T2 second, T2 by 2, here you stay for T1 seconds, go back and stay for T2 by 2 seconds, again 2, 1, 2, 7 is possible. So, all these ideas that you have for a 2 level inverter can be extended. So, this is 1, 0, 1, 2 and this is also you have 2, 7, 2, 1. So, all these bus clamping sequences can now be extended. So, given a 3 level inverter, that reference vector, you identify the nearest pivot vector and subtract that, you get your reference vector corresponding to the conceptual 2 level inverter. So, it is a conceptual 2 level, you can view this as a 2 level inverter. So, for this you can calculate your vector times T1, T2 and Tz, and like we did before, we can use either of the 2 pivot states, or we use only one, and then we can also do this division of active state time, we can apply one of the active states twice. So, this is advanced bus clamping PWM, which has been extended for 2721 now. So, all this what will they do? They will give you the same fundamental voltage, but the harmonics will change. How to study that? One simple way is to look at the error vector, like we did in the 2 level case now. So, this is the error reference that you want, this is the V beta that I was talking about actually. So, you can actually consider this as the V beta and this angle as your beta. Okay. So, now this error is the negative of that, this now is when you have applied the pivot vector. When you have applied the active vector 1, then this is the error voltage vector, when you have applied active vector 2, this is the error voltage vector. Now, what you need to do is you have to integrate this error voltage vector, and that will give you the stator flux ripple vector, which is a measure of the current ripple. So, this is straightforward, this is an extension of the analysis that you have really done for a 2 level inverter now. So, with this analysis, it is possible for you to compare the different PWM methods, compare the different switching sequences. So, one thing which has actually been done is, for example, such a study has been done and you have these things extended here. So, you have some So, the study has extended and it has shown that you have sequences, for example 0, 1, 2, 1 is better here and 7, 2, 1, 2 is better here, and so on and so forth, and here some 1, 0, 1, 2 and this is 2, 7, 2, 1. So, this kind of an analysis has been done, and you also have hybrid PWM methods which have actually been developed. So, many of these ideas are actually the novel switching sequences are discussed extensively in this paper. This is a very recent one on IEEE transactions on industrial electronics, and this thesis talks about these things in good detail on this advanced bus clamping PWM and how you would evolve hybrid PWM methods. So, this practically brings us to the most of the things that we really wanted to discuss here. So, So, if we look at what are the various things that we really looked at. So, it is about power electronic converters. Why do we need power electronic converters? That was our starting point. What is that is you may have your DC, you may have your load and you may have your supply. The supply and the load, they may not have the same requirement. For example, the load might be requiring AC, whereas your supply might be requiring DC. So, in such a kind of a situation you require a power electronic converter now, and there are the very most fundamental of the power electronic converters we look at are DC converters, and we looked at primarily DC AC converters, which are actually extensions from those DC converter now. So, we try to look at these topologies from DC converter. So, a DC converter, if you look at a buck converter or a boost converter, essentially it had a single pole double throw switch. We used the same single pole double throw switch and we realized 3 phase inverters, and we also looked at voltage source inverters and we looked at current source inverters. So, we basically reviewed the topologies, and the basic idea as far as those topologies are concerned are you are connecting switches. In power electronics, what you have other than R, L and C, you have switches. This is something that I have mentioned in the previous lectures. I feel it worthwhile to read again. You connect it in such a fashion that you normally have single pole double throw, single pole multiple throw switches, and the poles always have the current step elements in series, and the voltages have the the throws have the voltage step elements across them. So, that is how you normally have. In a voltage source converter, you have the voltage source available across the 2 throws. If it is a 3 level inverter, you have 3 different throws and you have the voltage source available across that, and the pole is usually a load terminal now. So, this is what you really do, and you come to this now. So, once you have a power electronic converter, you have a basic DC to AC converter. It can be 2 level or it can be 3 level. One of your first things that what you want to do is you want to control the fundamental voltage. You have your DC bus voltage from 600 volts. With 600 volt DC bus, it might be possible for you to realize some AC voltage, like whose peak line voltage is actually 600 volt. To that extent it is possible for you to do that. So, you want to control the fundamental voltage. So, that is one of the primary purposes why we did this particular course now. You have a voltage source inverter, and we have voltage source inverters, we have current source inverters. This course we have focused on voltage source inverters, and why? Because they are more popular now. You have these devices like IGBTs and MOSFETs, and they come with anti-parallel diodes, and they can conduct in both the directions while they can block voltage in only one polarity. In the earlier era we had thyristors, and thyristors are very rugged devices. They can block voltages in both directions but conduct in one direction. So, they were actually suited more for current source inverters. So, current source inverter and thyristor, they go better with one another now, but the thyristors take too long to commutate, and there have been many issues about commutation. You need additional commutation circuit and so on and so forth now. Whereas, now the modern devices are easy to turn on and turn off, like IGBT. They can also handle 1000 or 2000 volts, 1700 volts or so, and handle hundreds of amperes. So, it's good. So, you have a good current capability and you have IGBTs, and so therefore, we have been looking at voltage source inverter, and with this voltage source inverter we have been looking at how to control the fundamental voltage. What you have to bear in mind is there is no unique way of doing it, there are multiple ways of doing it now. So, what we try to explore is some multiple ways how exactly you can go about doing, and these multiple ways will give you the same fundamental voltage, but they will give you different harmonics, and that would mean that your RMS current is different, and that means your losses are different. That could mean your pulsating torque is different when you are applying in a motor drive, and the other important thing is these different PWM methods could mean your power conversion efficiency could also be different. So, this PWM has a very significant effect on the waveform quality and the power conversion efficiency. So, we have tried to look at the various aspects related to PWM, and we have analysis, and we tried to design a few PWM methods and so on and so forth. So, we focused on voltage source inverters for the reasons I told you. We looked at 2 level and 3 level inverters. We stopped beyond that because only 2 level and 3 level inverters are commonly used in the industry outside. So, I hope that you had useful outputs here, and this is very closely related to the work that we do here at the Indian Institute of Science. I would acknowledge all the members of power electronics groups past and present at the Indian Institute of Science who have contributed to this work, and it was a pleasure teaching this course here, and it's a pleasure giving these 40 lectures, and I hope that you enjoyed these lectures, and do let me have your feedback on these lectures whenever you have a chance to. Thank you very much.